You glance out the window in the morning and wonder, what's the chance of rain today? With nothing else to go on, you might say, oh, maybe 30%. Then a friend walks past carrying an umbrella. Nothing about the sky has changed, but suddenly your estimate jumps. Now it feels more like 80 or 90%. The weather didn't move. Your information did. Updating a probability the moment new information arrives is the whole idea of conditional probability. Written P of a given B. Picture every possible outcome as a point inside this rectangle. The whole rectangle is the sample space S. Two events live inside it. Event A in gold, event B in blue. Where they overlap sits the event A and B, both happening at once. In green, that's a intersect B. Now the crucial move. Suppose I tell you B has definitely happened. Every outcome outside B becomes impossible. So we dim it away. B is now your entire world. Inside that shrunken world, the only way A can still happen is through the part of A that lands in B, the green overlap. So the chance of A given B is just how big that green piece is compared to the whole of B. Turning that picture into symbols gives the definition. The probability of a given B equals the probability of A and B together divided by the probability of B. Read it as shrinking the world down to B. The top, P of A and B, is the overlap we still care about. The bottom, P of B, is our brand new total, the size of the world we're now in. One condition is non-negotiable. You are dividing by P of B, so P of B must be strictly greater than 0. If B can never happen, conditioning on it is meaningless. P of a given B is simply undefined. The definition has a hidden gift. Take it and multiply both sides by P of B. The denominator cancels, and out drops one of the most useful identities in probability. This is the multiplication rule. To get the chance that A and B both happen, take the chance of B and multiply by the chance of a once B is known. And since A and B are interchangeable, you can start from either event. Both expressions describe the very same joint probability, two honest roots to the same corner of the picture. There's one beautiful special case. Sometimes knowing B tells you nothing new about in mind. When P of a given B is just P of A, we call A and B independent. Feed that into the multiplication rule, and the conditional vanishes. The joint probability collapses to just P of A times P of B. Whenever you see that clean product, independence is quietly being assumed. When an experiment unfolds in stages, there's a picture that makes the multiplication rule almost automatic. The probability tree. Let me build one for drawing two balls from a bag, one after another. Start at a single root on the left. The first draw splits into two branches. First ball red, with probability 4 out of 10, or first ball blue, 6 out of 10. Write each probability right on its branch. Follow the top branch, a red first. One red is gone, leaving 3 red and 6 blue among 9. So a second red is 3 over 9, a second blue 6 over 9. The numbers change because we are drawing without replacement. And here's the rule the tree hands you. To find the probability of a whole path, you multiply the branches along it. Red then red is 4 tenths times 3 ninths. The multiplication rule, drawn as a road you walk. Let's put the tree to work. A bag holds 4 red balls and 6 blue 10 in total, and we draw 2 without replacement. Let A be first ball red, C be second ball red. We want the plain chance C is red, and the chance C is red given A. Start with the easier one, P of C given A. We're told the first ball came out red, so 1 red is gone, 3 red and 6 blue remain, 9 balls. The chance the next is red is 3 over 9, which is 1/3. Now the subtler question, P of C on its own. This is trickier, because whether the second ball is red depends on the first, which we don't know. So we split into the two cases the first draw could take: first red, 2/5, or first blue, 3/5. In each case, the conditional is easy. If the first was red, 3 reds remain of 9. So P of C is 1/3. If the first was blue, all 4 reds remain of 9. So P of C is 4/9. Now we weight each case by how likely it is and add the chance of first red times red given red plus the chance of first blue times red given blue. Substitute the numbers. 1/3 times 2/5 is 2/15. 4/9 times 3/5 is 12/45, which is 4/15. Add them. 6/15, which is 2/5. So the plain probability the second ball is red is 2/5. Exactly 0.4. Precisely the probability the first ball was red. Yet told the first was red, it drops to 1/3. The information genuinely changed the number. That weighting dadding trick has a name: the law of total probability, and it rests on the idea of a partition. A partition slices the whole sample space into cases B1, B2, and so on, mutually exclusive and exhaustive. Exactly one of them must occur. Now lay any event A across those slices. A gets carved into pieces, one inside each case. Since the slices don't overlap, the total chance of A is simply the sum of those pieces. Written out, A is the union of its pieces, one per case. Since they don't overlap, P of A is the sum over every case of P of a given BI times P of BI. Split into cases. Solve the easy conditional in each. Weight and add the entire recipe. A second, richer example. 3 warehouses supply the same product. Warehouse 1 ships half of all units, 2% defective. Warehouse 2 ships 30%, 4% defective. Warehouse 3, 20%, 5% defective. Let D be the event a random unit is defective. Two questions. First, what fraction of all units is defective? And second, the interesting one, if a unit is found defective, how likely is it came from warehouse 2? Part 1 is pure total probability. The 3 warehouse partition every unit. Each unit comes from exactly 1. So P of D is the sum of defect rate times supply share across all 3. Plug in 2% of a half is 1%. 4% of 30% is 1.2%. 5% of 20% is another 1%. Add the 3 and P of D is 0.032. So about 3.2% of all units are defective. Part 2 goes the other direction, from a defect back to a warehouse. Straight from the definition, P of W2 given D is the joint probability, W2 and D, over P of D. We already know the bottom, 0.032. The top is the warehouse 2 term from a moment ago, 4% of 30%, which is 0.012. Divide. 0.012 over 0.032 is 12 over 32, which tidies to 3/8, 0.375. Now savor this contrast, the most misunderstood point in the whole topic. The chance a unit from warehouse 2 is defective is 4%. But the chance a defective unit came from warehouse 2 is 37.5%. Same two events, wildly different numbers. P of a given B is not the same as P of B given A, never swap them. Your turn. Two machines make the same part. Machine 1 makes 60%, 5% defective. Machine 2 makes 40%, 10% defective. Find the overall probability a random part is defective. Pause here and try it before I do. Here's the walkthrough. The two machines partition every part, so it's the law of total probability again. P of defective is 5% of 60% plus 10% of 40%. That's 0.05 times 0.6, which is 0.03, plus 0.1 times 0.4, which is 0.04. Add them, the overall defect rate is 0.07, 7%. If you landed there, you've got this. And as a bonus, a defective part came from machine 1 with probability 0.3 over 0.7, 3 sevens. Trap 1. The deadliest. Confusing P of a given B with P of B given A. Always pin down which event is the given before you write anything. Trap 2. Forgetting P of B must be greater than 0. You're dividing by it. If the condition is impossible, the conditional doesn't exist. Trap 3. Overlapping cases in total probability. The cases must be mutually exclusive and exhaustive. Overlap. And you double count past one. And trap 4. Multiplying as if events were independent. That clean product only holds when they truly are. If B changes A, use the conditional. Let's lock it in. Conditional probability shrinks the world to B. P of a given B is P of A and B over P of B, always with P of B above 0. Multiply through for the joint probability, two equivalent ways. The multiplication rule. And when it collapses to P of a times P of B, that's independence. And to build a probability from cases, use total probability, split into a partition, solve the easy conditional in each, wait, and add. Define your events, spot the given, pick the right tool, and conditional probability will never trip you up again.